each lesson, we're kind of adding in another factor to our calculation. So we started out where we looked at rate versus concentration with our differential rate laws, and then we brought in the factor of time versus concentration with our integrated rate laws. And what we're going to look at now is bringing in the temperature and our orientation. Because if you think back, we talked about our collision model, and they have to collide with sufficient energy, and they have to have proper orientation. So this last calculational thing is going to kind of bring in the temperature and our orientation. The one thing to remember about the rate constant, and I know I've had several people ask me questions, well, okay, in this problem, why is it giving me temperature? Do I have to use temperature? Well, typically no, but the rate constant is temperature dependent. So as long as you are performing the same reaction at the same temperature, you're going to use the same rate constant. But if you change the temperature, that is the one thing that will change the rate constant. So kind of keep that in mind as we're working through here. But we're going to talk a little bit about the theory, and then we're going to be using some problems that are in a file that's called Arrhenius Made Easy. In that file, it has multiple pages where it talks to you again about kind of the Arrhenius equation, and it also, those of you that are going to be using TI-84s, it also steps you through how to do the Arrhenius calculations with the TI-84s. Okay, so we're going to go in here and take a kind of a look here. So here we are, and this is just kind of some little visuals here. So here it's talking about with the effective temperature, and here if it's less than the minimum amount of temperature in part B, we don't get a reaction to form products. They just kind of bounce off of each other. And then going back to our, whoops, oh, sorry about that. Going back to our energy diagrams, remember we had those, so this minimum energy, all right, say it's, we'll just do an example of an exothermic. And so remember that it's that minimum energy is the energy difference between where the reactants are and where the top of the hill, which is our activated complex. And so this here is E sub A, or activation energy, kind of what in this diagram they're referring to as E minimum on there. Now, in looking at this, we haven't looked at these graphs before, but one thing to note about these, this is a graph, and it's looking at the fraction of molecules and then what their specific kinetic energy is. So if you remember when we talked about the relationship between the kinetic energy of molecules and the absolute temperature, remember we said that the absolute or Kelvin temperature was directly proportional to the average kinetic energy. And so remember that it's proportional to the average. So not all the molecules, if the substance is at a given temperature, not all the molecules are going to have the same exact kinetic energy. And then one thing also to note, and this is just doing a plot of the fraction of molecules that if they collided would result in a reaction going forward. And the thing to note here is that kind of look at the distribution of the kinetic energies at low temperature versus a high temperature. And what you should see is that as we increase the temperature, that the distribution of the kinetic energies actually broadens out. So at lower temperatures, we have a much narrower peak, like right here, okay? And so we have a smaller range of kinetic energies, whereas at a higher temperature, let me just put a here, oops, that is not a highlighter. Let's go back up here. There we go. So here, when we get to a higher temperature, See how that we get a wider distribution of kinetic energies. And then the other thing to note is that, which is kind of the purpose of this graph, I'm just sort of pointing out some other things, is that if this is our activation energy, what we'll see is we get all of this, a lot more of my particles would be capable of having a collision that would have enough energy for the reaction to go forward. The frequency factor that is involved in the Arrhenius equation, that is basically, if you looked at the three-dimensional region, the volume around a molecule, and you took what fraction of that volume that another reactant molecule could approach in, that would result in a proper orientation for a successful collision, that's kind of what it's looking at. So that's sort of the way to think of it. It's looking at what is the proportion of the ways that another molecule could approach that reactant molecule that would result in proper orientation for a successful collision. All right, at this point, even though there are some additional problems in your notes, and we'll come back to those, but I want to switch over to the Arrhenius Made Easy document, just to kind of show you what's in there, and then also because I like the problems that are in that document. So we're going to just pop over here. I'm going to look at the Adobe file first, and then we'll go and look at kind of the equations that they give us in there. So if you go down to about page number 3, you'll see that it's giving us the Arrhenius equation, and this is in a y equals mx plus b format. So let me switch back over to my OneNote so we can look at that. Okay, so in this y equals mx plus b format, what we want to do is, let me go back to draw, get my pen. There we go. So remember, we're dealing with a lot of graphs in this kinetics chapter, and what we want to see here is that in this format, we're plotting the natural log of the rate constant versus 1 over the Kelvin temperature. And what Arrhenius says is that when I plot natural log of the rate constant versus 1 over the temperature, then I get a line, it's a linear relationship, where the slope of that is equal to the negative activation energy divided by R. Now, this R is the energy version of R. So this R is our 8.314 value, and that is, I believe, joules per moles Kelvin. Okay, so on that, using that R value, all right, then we can, from our slope of our graph data, we can find the activation energy for the reaction. Okay, the other thing is that if it ever asks for frequency factor, that the y-intercept is the natural log of the frequency factor of this line. So we can get the frequency factor if we need it. Now, you will have some problems where maybe they give you just 2 points and ask you questions about it, or they'll give you one rate constant temperature combination and maybe give you the activation energy and ask you to find what the rate constant would be at another temperature. This is a really handy form of the equation. I'm not going to go into the algebra to derive it, but it's not that hard to derive if you want to try that yourself. But this is an algebraic equation. Good to know on there. It's not on the formula sheet. Okay. So, but this will help you in doing some of the problems, especially some of the quest problems.